Imagine dropping from orbit at 17,000 miles per hour, locked inside a 20-ton mech. That's the same mass as NASA's Orion crew module, but you're not in a sleek capsule. You're in a walking tank, hurtling through the atmosphere. The air in front of you compresses so fast it heats up beyond molten lava, threatening to strip metal and cook anything inside. Now add the crushing force. Your body faces G-forces that push the limits of human survival, far beyond what any fighter pilot endures. Could any human survive this ride? Today, we'll tear apart the physics behind a Titanfall drop. Heat, G-forces, and impact. Let's see exactly when your body would fail and why even the toughest Titan can't save you. To understand why a Titanfall drop is so deadly, you need to know what happens when anything slams into Earth's atmosphere at orbital speed. The physics of atmospheric entry are brutal. At 17,000 miles per hour, you're not just falling, you're punching through air so fast it can't get out of the way. Molecules pile up, compress, and the temperature around you soars past molten lava. This isn't just friction, it's a shock wave that turns the air itself into a wall of fire. NASA's Allen and Eggers figured out the secret back in the 1950s. Blunt shapes save lives. A rounded heat shield makes air slow down and pile up, forming a cushion that pushes the hottest plasma away from the vehicle. That's why real spacecraft look like flying saucers, not fighter jets. But a Titan's sharp, armored body? It's the opposite of what you want. Those hard angles focus heat instead of shedding it. Here's where the real difference kicks in. Spacecraft don't rely on thick armor. They use ablative heat shields. These are made from materials like Avcoat or Pica, designed to char, melt, and vaporize on purpose. As the outer layers burn away, they carry heat with them, protecting what's inside. The Apollo Command Module's heat shield was a glass-filled epoxy that slowly ablated during re-entry. The Orion capsule uses a modern, reformulated Avcoat for even better protection. Stardust's Pica shield was only about 8 centimeters thick, but it was enough to handle speeds over 12 kilometers per second. A Titan's metal plating? It's built for bullets, not plasma. Metal conducts heat straight through. Without ablation, the cockpit would spike past 300 degrees Celsius within seconds, hot enough to destroy electronics and cook a pilot alive. Spacecraft swap armor for ablators, trading brute strength for controlled sacrifice. If you tried to add enough heat shielding to a Titan, you'd double its mass and turn it into a useless hulk. And this is just the first hurdle. Even if the mech somehow survives the firestorm, the real test comes next. What happens to the human inside when the forces of re-entry hit full blast? G-forces are the silent killer in any high-speed descent. At 12 Gs, your 150-pound body weighs 1,800 pounds. That's not just uncomfortable, it's a crushing load that your bones, muscles, and organs aren't built to handle. Fighter pilots, using G-suits and muscle straining, can survive up to 9 G for a few seconds. But even the best trained pilots lose consciousness if the force lasts too long. NASA's re-entry profiles for Apollo and Mercury kept astronauts under 8 G, and even then, the capsules were engineered to spread out the load. In a Titan, the rigid, upright seat would channel every shock straight through your spine and chest. Deceleration is where things get deadly. As the Titan slams into denser air, the force spikes fast. Your rib cage can't expand, your diaphragm can't contract, and blood pools in your legs. Within seconds, your vision narrows to a tunnel, then fades to black. Sustained G-forces above 10 G overwhelm even the best G-suits. They're designed to squeeze your legs and keep blood in your brain. But past that threshold, the suit can't compensate. At these levels, you'd lose consciousness in under 10 seconds, and without immediate help, survival is measured in minutes. The duration of the force is just as critical. Pilots in high-G maneuvers only experience these loads for a few heartbeats. A Titanfall drop, even assuming some atmospheric braking, would stretch that punishment over minutes. Research shows that a constant 16 G for 1 minute is fatal. Even at 12 G, the odds aren't much better. Your heart can't pump against the crushing weight, your lungs can't fill, and organ failure sets in fast. Negative G is even more unforgiving. A sudden -3G maneuver floods your field of view red before you black out, as blood rushes to your head and bursts capillaries in your eyes. Mercury astronauts avoided this with careful re-entry angles and constant monitoring. Titans, with no such safeguards, leave you exposed to the worst-case scenario. Modern spacecraft use computers to plot the safest descent, keeping G-forces within human limits. Early capsules relied on ground-based calculations and careful piloting. But a Titan's free fall is uncontrolled. Peak forces can spike without warning, and there's no automated system to save you. Even if you're tough enough to stay conscious, the crushing force never lets up. And if you somehow make it through, there's one more hurdle waiting below. The speed you reach before impact isn't just a number. It's the final line between survival and total destruction. When you drop a 20-ton Titan from orbit, the question isn't just how fast it falls, it's whether anything can slow it down before disaster. That's where terminal velocity comes in. Terminal velocity is the maximum speed an object reaches when the pull of gravity is balanced by air resistance. For a human skydiver, lying belly to Earth, that's about 55 meters per second, roughly 120 miles per hour. But a Titan, with a dense, streamlined body and very little surface area compared to its mass, it would hit nearly 900 miles per hour before drag could catch up. Shape matters. A parachute spreads out, grabbing as much air as possible. A Titan, built like a bullet, slices right through. Even the world's fastest animal, the peregrine falcon, maxes out around 200 meters per second in a dive, less than a quarter of a Titan's speed. The difference is all about mass versus drag. The heavier you are and the less area you present to the wind, the faster you fall. Now, let's look at the numbers. At nearly 900 miles per hour, about 400 meters per second, a 20-ton Titan carries enormous kinetic energy. The math: kinetic energy equals half the mass times velocity squared. That's 0.5 times 20,000 kilograms times 400 meters per second squared. You get roughly 1.6 billion joules. That's enough energy to level a building. And the real danger comes in the last moments, the instant before impact. Without retro rockets or parachutes to slow the fall, the impact shock is brutal. When a rigid object, like a Titan, hits the ground at terminal speed, the deceleration spikes to hundreds, even thousands of G units. No human body can survive that. Research shows that even the most extreme crash survivals top out at about 100 G for a split second. A Titanfall landing would shatter that limit many times over. Altitude changes the story, but not in your favor. Skydivers accelerate gradually, reaching terminal velocity in thinner air before slowing in denser layers. Titans drop from low orbit and hit thick atmosphere almost immediately. The result is a violent, rapid deceleration, like colliding with an invisible wall. If you imagine the Titan somehow surviving the descent, the pilot inside faces an even bigger problem. Every force, heat, G's, and impact hits at once. The real question isn't if you'd survive, but which of these killers would get you first. Heat, G's, and impact. These are the pilot's nightmare in a Titanfall drop. First comes plasma cooking. Without the real heat shield, the cockpit turns into an oven. The temperatures soar beyond what any electronics or human could tolerate. Next, G-force collapse. As the Titan slams into dense air, the pilot faces crushing acceleration, pinning them in place and shutting down vital organs. Finally, fatal impact. All that kinetic energy has to go somewhere, and it ends in an instant, with forces that no crash system can absorb. Real spacecraft stack the odds in the crew's favor. Capsules like Apollo or the Atmospheric Re-entry Demonstrator carry hundreds of ablative tiles, weighing over a ton. Machines dedicated to shedding heat, not trading blows. Their layered defenses work together. Heat shields burn away gradually. Parachutes slow the final descent, and the blunt capsule shape spreads out the heat and force. Even a one-person escape suit, like GE's Moose, demanded foam, a heat shield, and parachutes just to give a lone astronaut a fighting chance. Scaling that up to a 20-ton mech is unthinkable. The Titanfall approach skips every safeguard. No ablative shield, no staged slowing, no crash couch. The drop isn't a controlled landing. It's a 2-minute free fall with all the worst physics compressed together. For Apollo, the descent from orbit took about 15 minutes, with peak heating lasting 90 seconds and maximum G-forces around 7 for half a minute. Inside the Titan, the pilot would face higher Gs for longer, and the cockpit would spike to lethal temperatures in under half a minute. There's no time for the body to recover, and nowhere to hide from the punishment. Best case, the pilot never feels the end. The Titan's legs can't absorb the energy of a 20-ton fall at nearly 900 miles per hour. Even with advanced crash cushions, humans can't survive impacts above 100 G for more than a millisecond. A real Titanfall landing would deliver hundreds of Gs, enough to erase any chance of survival. Every real-world solution, thick ablative shields, retro rockets, crash couches, and parachutes, adds weight and complexity that Titans simply don't have. Reality demands trade-offs, and every safety upgrade costs mobility, firepower, or both. The ARD's small heat shield alone weighed over 1,000 pounds. Scaling up for a Titan would mean tons of extra material, making combat impossible. In fiction, the drop is pure adrenaline, but in real orbital mechanics, there's no margin for error and no way out. So how does Titanfall's iconic drop stack up when you pit sci-fi spectacle against hard physics? Let's break down just how far reality diverges from the game's adrenaline-fueled freefall. In Titanfall, the mechs plummet straight from orbit. No heat shields, no parachutes, no slowing engines. Just a direct shot toward the battlefield. It's a move built for cinematic impact, not for survival. In the real world, every re-entry from orbit is a carefully choreographed process. The Mercury program proved that even a single astronaut needed layers of protection. Ablative heat shields that sacrifice themselves, parachutes to bleed off speed, and a capsule shape calculated to spread the heat and force. These aren't optional extras. They're the only reason anyone walked away from those missions. The concept of ablative shielding dates back to Robert Goddard in the 1920s, and it's still the gold standard. Each gram of shield is designed to burn away, carrying heat with it. Titanfall's mechs, by contrast, are all armor. Great for bullets, but a death trap for re-entry. Metal traps heat, it doesn't shed it. Try to fudge the numbers. Halve the Titan's speed. Drop it to 8,500 miles per hour. That lowers the heat load, but you're still facing temperatures and deceleration forces that would destroy both machine and pilot. Even slower re-entries heat the mech to deadly levels without ablative armor. G-forces might dip to 6G, but that's still enough to knock out a human in seconds if it lasts. Real astronauts only saw those peaks for a blink. A Titanfall drop would drag them out far longer. And the final impact? Even if you somehow solve the heat and Gs, you're still slamming into the ground with more energy than a small bomb. Fiction skips the messy, multi-stage deceleration real engineers spend years perfecting. Modern capsules use a series of parachutes, retro rockets, and carefully planned trajectories to bring both heat and forces down to survivable levels. Titanfall's mechs just fall and hope. Even space debris like the mysterious WT-1190F follows the laws of physics, burning up and breaking apart as it re-enters. Titanium oxide signatures in the air don't care if you're a lost probe or a 20-ton robot. So, could you make a Titanfall drop survivable? You'd need to slow down, add real heat shielding, and stage your descent in steps. But at that point, you're not doing a Titanfall drop anymore. You're running a cautious, 15-minute re-entry, like the space shuttle, with thousands of thermal tiles and a long, careful glide. The 2-minute fiery plunge just can't work with human bodies and real materials. But that's the whole point of sci-fi, to bend the rules. Give us something wild and make us ask, what if? So here's your challenge. Think you can outsmart physics? Got a theory, an alien material, or a tech fix that could make a Titanfall drop possible? Drop your wildest ideas in the comments, and remember, sometimes the impossible is what makes the story worth watching. The reality is simple. Titanfall drops break every rule of real-world physics. Studies show that 10 to 40% of satellites' mass can survive re-entry and reach Earth's surface, usually as shattered debris, not intact machines. If a full-sized mech made it down, the results would be catastrophic for anything in its path. Real spacecraft survive by sacrificing heat shields and slowing down in stages. Titans do neither. Even for random space debris, the odds of injury are astronomically low, but strapping yourself into a falling mech isn't just risky, it's certain death. Heat, force, impact. Pick any. You lose.